Hello everyone, welcome back. In this particular video, we're going to start talking about the reactions of carbonyl compounds. And we're going to continue doing this for the next series of videos where we're going to explore different reactions of carbonyl compounds. To kick off, what we're going to do is we're going to look at what's called the hydrate formation. Okay, this is the first reaction that we're looking at. And hydrate formation involves the reaction of a carbonyl compound with water. Okay, so this is the reaction with water. And the product, when a carbonyl compound reacts with water, the product that you get is called the hydrate. Now, hydrate, again, that's just a generic name. Okay, it's not a specific name. So any carbonyl compound, when it reacts with water, you get the hydrate of that carbonyl compound. Okay, so this is the carbonyl compound, and it gives us the hydrate. Now, as you notice, what happened here is basically the water adds to that carbonyl carbon, and you get two hydroxyls on that carbon. So the carbonyl carbon here, that carbon is this carbon where the two hydroxyl groups are attached. Now, this reaction, as you can see, is in equilibrium. So it can go forward and it can go backward. And in fact, in a little bit, we're going to look at the mechanism of these reactions. How does it go forward and how does it go backward? We're going to look at both mechanisms. Now, the position of the equilibrium really depends on the carbonyl compound. As we've seen earlier, ketones, they're not very reactive for steric and electronic reasons. So for ketones, the reaction actually favors the ketone instead of the hydrate. So the hydrate is not favored at equilibrium. There's a lot more of the ketone present at equilibrium. Aldehydes are going to participate more favorably in this reaction. And for something which is a very simple aldehyde like formaldehyde, the equilibrium actually favors the hydrate, as you can see from these arrows. So there's less of the formaldehyde and more of the hydrate at equilibrium. Again, I'm not quantifying these things, but again, it really depends on the particular ketone or the particular aldehyde that we're looking at. In case of formaldehyde, this is a highly favored reaction. So you might get like upwards of 90% of the hydrate under these conditions. Okay. Now, the rate of this reaction, the hydrate formation reactions, if you do it under neutral conditions, that means if you just take the carbonyl compound and add water to it, the rate of the reaction is really slow. And you can actually enhance the rate, speed up the reaction by using a base or using an acid. So under basic or acidic conditions, the rate is enhanced. So you can reach equilibrium faster. Now, again, I want to clarify here. Enhancement of the rate does not mean that you're going to make more of the product. That's not what we mean. It essentially means that you will get to the equilibrium faster because it's going to, the base or the acid, it's going to enhance the rate of both the forward reaction and the backward reaction. So you will have more, you will get to the equilibrium faster under these conditions. So what we're going to do next is explore the mechanism of this hydrate formation, and we're going to look at the mechanism under both basic and acidic conditions. So we'll continue on with our discussions, and we're going to look at the mechanism of hydrate formation under both basic and acidic conditions here. So under basic conditions, you would have the carbonyl compound, and since this is the reaction with water, under basic conditions, what that means is you're going to have hydroxide and you will have water present. Okay, they will both be present. So that's the basic condition. And you will get the hydrate. Now, under these conditions, as we've previously discussed, whenever you're under basic conditions, the first step in the reaction mechanism is a nucleophilic attack. So the first step what that's going to happen is your base, which can serve as a nucleophile, it will go and attack that carbonyl carbon. Simultaneously, the double bond would open up and electrons would be pushed to the carbonyl oxygen. So this would give us R with a hydroxide and an oxygen with a negative charge on it. So it brings us to this tetrahedral intermediate. And from the tetrahedral intermediate, the alkoxide here, okay, this oxygen can now go ahead and get protonated. And that's going to give you the hydrate, plus it's going to give you hydroxide when you look at the mechanism overall. It will give you hydroxide there. Okay, so, and now when we write the reaction itself, we don't have to show it, but it will give you the hydrate. Now, probably to actually make it better, to remove any confusion here, I will just write it straight down here. So we have the water, which is the other fragment that's present here. And so the oxygen picks up a proton and it brings you to the hydrate. And plus, you're going to generate hydroxide. And as you can see, that hydroxide can go and start this reaction again. So what that means is you don't really need a lot of hydroxide here. Just a catalytic amount of base is more than enough to get this reaction started, because it gets used up initially and then you generate it in the end. So it can cycle back and do the reaction over again. So that's the mechanism under basic conditions, where the first step is the attack. Okay, so the first step is the nucleophilic attack. And then the second step is the proton transfer, or a protonation step. Under acidic conditions, the same reaction is going to look a little different. Okay, and so now since we are under acidic conditions, we can write a hydronium ion here. And realize hydronium ion is nothing but acid and water. That's what we're talking about here, just a hydronium ion. And our product is again going to be the hydrate. Okay, it's the same product, whether you're under acidic or basic conditions. And similar to what we've discussed earlier, under acidic conditions, the first step is always going to be a protonation event, so that carbonyl oxygen is going to get protonated. Okay, because recollect, we need to convert this weak electrophile into a more stronger electrophile. Okay, stronger, relatively stronger electrophile. So that carbonyl oxygen gets protonated. You get that species. Along with that, you're generating water, but water is there in the system because you're going to do this reaction under aqueous conditions, because this is the reaction with water. And so once you get that, then the nucleophilic attack happens. So the second step, so first step is a protonation. Second step is the nucleophilic attack. Okay, so when you have that nucleophilic attack, you get R hydroxyl. Okay, that's this oxygen. And then the water molecule came in and it's connected to that carbon through that oxygen atom, has a formal charge on it. And then finally, recollect there is a final proton transfer step. So in the last step, another molecule of water comes in. It's going to deprotonate. It's going to deprotonate to give us the hydrate. Sorry, the hydrate plus, you're going to get H3O plus back. So very similar to the base catalyzed conditions. Notice how the acid is regenerated. So you consume the acid to begin with, and then you regenerate it. That means, again, you don't need a lot of acid here. You just need a catalytic amount of acid for doing this reaction. Okay? So that's the mechanism of the reaction, both under basic conditions and acidic conditions. Now, these hydrates, like we saw, they exist in equilibrium with the carbonyl compound. That means this hydrate can also go back to the carbonyl compound. So in a later video, we're going to actually look at the mechanism of how the hydrate is converted into the carbonyl compound, the electron push mechanism for that. But for a start, that's the reaction of carbonyl compounds with water that gives a hydrate as the product. Bye.